Hi guys! When we think of our built environment, our skyscrapers, bridges, and underground water networks, we think of them as permanent monuments of human engineering. We build them out of steel and reinforced concrete to withstand massive physical forces. Yet, some of the greatest threats to these massive structures are completely invisible to the naked eye. As you can see, our beautiful introductions, right? So now, welcome to our presentation on the effects of the microbes in the built environment. Today, we are diving deep into a phenomenon known as a microbiologically influenced corrosion, or MIC. While environmental factors like moisture and oxygen cause standard chemical rust, microorganisms can accelerate this destruction by up to 1,000 times. So now, over the 10 minutes, our group will analyze how specific bacteria target urban infrastructure, the exact biochemical mechanism they use to dissolve metal and concrete, the real-world failures they cause, and how modern engineering is fighting back. Let's hand it over to the next person to look at the microscopic culprits behind this destruction.
Hi, Assalamualaikum. My name is NABILA HUDA and I will act as microbial specialist that responsible for explaining the specific microbial threats, biological mechanism, and chemical equation. To understand how microbes cause rust and structural decay, we have to look at biofilms. Microbes in the built environment rarely act alone. They form complex, slimy colonies called biofilms on surface like the inside wall of water pipes or the crevice of steel beams. Inside this biofilm, two main groups of bacteria drive the corrosion process, which is sulfate reducing bacteria (SRB) and ion oxidizing bacteria (IOB). Let's look at sulfate reducing bacteria such as Bacillus fibrio. These organisms thrive in anaerobic or oxygen-depleted environment, which is it right at the base of the thick biofilm against a metal surface. SRB consume organic nutrients and utilize sulfate instead of oxygen for respiration. Their metabolic byproduct is hydrogen sulfide gas. This gas reacts directly with iron in steel, creating iron sulfide and stripping electrons away from the metals. This causes rapid, localized heating, literally boring holes straight through thick steel walls. On the flip side, we have aerobic ion oxidizing bacteria like Gallionella. These bacteria live in oxygen-rich zone and actively oxidize ferrous iron into ferric iron to extract energy. This process leaves behind thick orange-brown tubercles or rusty crust. These crusts create perfect oxygen pockets underneath them, allowing the anaerobic SRB to move in. Together, they form a destructive cycle that rapidly degrades metallic infrastructure. That's all from me.
Okay, so hello, I'm Farah. So I'm responsible for the real-world structural impact, case studies, and economic or safety consequences. Okay, so the biological processes explained by now may happen on microscopic level, but their impact on the built environment is huge. Microbiologically influenced corrosion, or MIC, does not only affect the appearance of structure. More importantly, it weakens their strength, reduce their lifespan, and can even create serious safety risks. One common example can be seen in municipal water and wastewater system, in sewage pipeline, sulfate reducing bacteria produce hydrogen sulfate gas, also known as H2S. This gas rise and come into contact with moisture on the inner surface of concrete pipe. Another type of bacteria called Aciditobacillus theocidans then converts the hydrogen sulfide into sulfuric acid or H2SO4. This process causes severe damage to the concrete and is known as biogenic sulfate corrosion. So, as the concrete continues to deteriorate, the steel reinforcement bar, commonly known as rebar, become exposed to moisture, oxygen, and microbial activity. The steel then starts to corrode and expand. Since rust occupies a larger volume than the original steel, pressure builds up inside the concrete, causing cracks and weakening the structure from within. Over time, this can lead to major problems such as leaking pipeline, sudden pipe bursts beneath road, contamination of water system, and in severe cases, structural failure. This issue not only affect public safety but also require expensive repair and maintenance work. In fact, corrosion costs the global economy trillions of dollars every year. And researchers estimate that around 20% of all corrosion damage is related to microbiologically influenced corrosion. That's all from me. Thank you.
Hi, my name is Muhammad FAHMI and I am responsible for explaining the mitigation or prevention strategies, collecting all video or audio assets and compiling the final 10 to 15 minute video for the submissions. As you can see from the previous video, because the built environment cannot simply be rebuilt every few years, engineers and microbiologists have developed advanced techniques to mitigate and prevent MIC. The first line of defense is material selection and surface design, applying specialized biocidal coatings, epoxy lining, or using corrosion-resistant alloy prevents biofilm from adhering to the surface in the first place. If bacteria cannot stick, they cannot form the microenvironment need to accelerate rust. The second method is chemical and physical maintenance, and here is the photo for the second methods. As shown on the photo, in water and industrial piping systems, regular mechanical cleaning using PICS devices and through pipes to scrape away scale combined with the target use of biocide chemical keeps microbial population under control. Additionally, engineers use cathodic protection by applying a continuous, low voltage electrical current to a metal structure. We can supply excess electrons to the steel. This forces the metal to act as a cathode, neutralizing the electron stripping chemical reaction driven by the bacteria.
So guys, we're on the last path. In conclusion, the built environment is not static. It is constantly interacts with the living world around it. Microorganisms like sulfate reducing and iron oxidizing bacteria demonstrate that even our strongest steel and concrete structures are vulnerable to biologically process. So guys, to understanding these microscopic interactions, allow modern civil engineers and microbiologists to work together, designing smarter materials and better maintenance protocol to safeguard our infrastructure. Thank you for listening to our presentation, and we welcome any question in the comment section below. Thanks guys.